So this might be a situation that you're familiar with. You're somewhere in a meeting, you're discussing something, you have your laptop with you, maybe you're taking notes, and then somebody brings up, oh, like this one thing is really, really slow in our application. And for that one thing, you need to repeat something, let's say 100 or 1,000 times. And you know, you're a good programmer, you're in that meeting already, so you're, I got this. I know what I have to do. So you're like, superhero programmer, let me fix this. So you pop up your interactive shell, and then you just copy and paste your current implementation of what your repetition logic looks like. So this is basically just a recursive function that executes another function n times. Okay, we got this. So now let's see how fast is this actually. So you make a timer call and you say like, okay, how long does this take to repeat this 100 times? And you find out just for the simple function that you put in, it takes 210 microseconds. Okay, cool. So, but what if recursion isn't the fastest thing? So you're like, okay, let's create a list. In a real application, we already have a list. And then we say, okay, let's just use enum each to iterate over it, and let's see how fast that is. And you do it, and it's 165 microseconds. And it's like, oh, that's faster. Interesting. And you run it a bunch of more times, and then it's like, oh, it's always faster. Best thing ever. So like, we're just going to switch the code out. We switch it to this one. Now, obviously, we're faster. So this is obviously like the biggest success. Like, was fast. We did it good. Everything great. And obviously, this is also the end of the talk, because obviously, this is how benchmarking is done. Everything is great. And you can all leave now. This is what I call efficiency. No, but actually, this is what I call like, I have no idea what I'm doing. There's so many things wrong with what I've just shown you that I can't begin to explain it. So here's just a couple of points of what was wrong in there. So we just took one sample of the recursive call. Like maybe something kicked in while we were executing that function. All of a sudden it was much, much slower, but normally it's faster. We don't know. Does the repetition actually matter? You know, like when you repeat a function 100 times, and that repetition is very fast, most likely your bottleneck is more what you do in that function and not the actual repetition. There's other problems like you were in a meeting, so your laptop was on battery power. And on battery power, it works much, much slower. So my laptop is about half the speed for CPU-intensive tasks when I am without battery power. So that's a huge thing. And yeah, you just do it in a shell. The shell is not your production environment. It has very different performance characteristics depending on your environment. And so you should never do that just in a shell. Also, it's not repeatable. It's not checked in into your repository. Nobody can rerun it. It's one of the worst things that I can see overall. But the sad thing is, I mean, I made this example up. But this is real things that people out there do. Like sometimes I write a blog post about benchmarking something, then somebody replies like, oh, but I executed this thing in my shell and it's much, much faster. And I go like, oh, where do I even start, right? So let's fix this. This is an actual benchmark that would do the problem. We increased the size of the list to 10,000 because we figured out that's actually what we need to and want to do. And then we have our enum each sample. So benchee is a benchmarking library in Elixir. And then we have the enum each example. We add a list comprehension in just for fun. And we have the recursion example. And what benchee will do is it will not only run each of these functions once, it will run them for a specific warm-up time, which we get into later. And then it will run them for another specified period of time. And then it will present you aggregated statistics about what happened. And so these are the results. I don't know how readable they are, but there's nice graphs that you can see up there. And we find out that actually recursion is the fastest by far. So our enum each that won out there by luck or poor chance or because of the environment was broken or whatever, is actually 1.6 times slower, and list comprehensions are over 2 times slower. We can see there's a bit of standard deviation going on, but that's fine. One thing, what I graph here is IPS, or iterations per second. I like to do that instead of the average, so that is how many iterations of this on average can I do per second. What's cool about iterations per second versus average, bigger is better. So when I give you a graph, and then the biggest graph is the best thing because it's the most performant one, as opposed to averages where you want to hit the smallest graph, sort of. That's not what you want to do. So we can see that running a proper benchmark, we get a completely different result for what is actually the best outcome. So this talk is titled Stop Guessing and Start Measuring. I'm Toby. You can find me on the internet as at Practop. I'm the tech lead at Elixir. I run the Ruby user group in Berlin, and I do a bunch of other things. And you might have, when you were scrolling through the speakers page, you might have noticed that I am Foxy, and the organizers here are actually very, very good organizers because I always send them a selection of pictures that they can choose from, and really good conferences obviously choose the Foxy picture because it's the best one. And organizers took it one step further here. They actually arranged everyone to look at Foxy. So you're in the center of attention talk, so to speak. And if you think I just put like one of these on and run around alone, it's no. I have my trusty unicorns with me when I do that. And if you look closer, you can actually find another speaker on this photo. But sorry, I have no onesie with me today. Anyhow, moving on with the real talk. A lot of talks either talk about one concept very broadly, but then it's very hard to bring it into your daily life, into your daily work life. On the other hand, other talks are very, very practical, talk about one tool very much in depth, but then it's hard to sort of apply that knowledge to another language or to something else that you want to do. And in this talk, I try to marry both. So we're going to talk about the high-level concepts, but I'll show you lots of examples, which mostly will be in Elixir and with the library benchee, which I'm the creator of and one of the maintainers, along with Devin, who is also here and gave a talk about small word networks in this room yesterday. Yeah. So before we go on, we want to figure out quickly what actually is benchmarking. So what is it that we do in benchmarking? And I have a little hope for you to remember what benchmarking actually is. Benchmarking is sort of like we have functions and we feed them some inputs. And what we actually want to measure is like how fast do these functions devour the inputs that I'm giving them. So in the case of these bunnies, we see what's up and how fast they eat it. But we can also see that sometimes, the inputs don't actually match the functions, so they have some problems digesting them. And then you actually need to be very careful because right about now, come on, Ghost, yes. You need to also be very careful with conditions that like your machine needs to just do the one thing because right now the resources here are clearly competing and so our other benchmarking functions can't really reach their full potential. You also need to be careful that they're not distracted. And so those are actually my bunnies. You can follow them at Berlin Bunny Trio, but yeah, I hope that helps you imagine what like functions are eating inputs and you want to see how fast they eat their inputs. And yeah, okay. So one other thing that I need to get out of the way is profiling versus benchmarking. And profiling gets you these flame graphs or something like this. And profiling is basically you have an endpoint or you have something that is slow, but you don't know what is slow. What do you need to make it faster? Then you can run profiling or sort of tracing to see like which function took the most time. So this is always like this function calls that function and so on and so on. And then you see like, okay, this one takes a lot of time. So if I can optimize this, I'm going to be better. That is very good and very helpful, but it adds a lot of overhead to what you're doing. So what I generally recommend you to do is do this to find, like, first run the benchmark to establish a baseline. How fast are you? Then you can run some profiling if you have no idea, like, what's wrong, to see like, what is actually the slowest partner. And then you improve it, and then you use your benchmark to verify that you actually got faster. So another big question that you ask yourself when we talk about benchmarking is, like, what do we actually want to benchmark? We want to benchmark runtime, memory, throughput, or maybe something custom. And the answer as to every question worth asking is it depends. You can make a genius benchmark with something custom. And my favorite example is this benchmark that the Phoenix team ran of how many concurrent WebSocket connections they can make to a single node. And they started out with, I think they were able to make 10,000, maybe 30,000 connections. And through iteratively making better, they were able to maintain 2 million WebSocket connections against a single node. And that even wasn't the end of the line because it was limited by the ulimit file handle they set in the beginning because they thought they would never reach 2 million or go over it. That is neither just runtime or memory, it's both of them combined. And so if you have a very specific goal, a custom benchmark is most likely what you want to go for. It's very worth a read. It's fascinating. We're going to talk mostly about runtime here, because runtime is sort of the most popular thing, and it's the easiest thing, and that's already enough to talk about in general. So one question that you might ask yourself when you benchmark runtime is, how long will this take, as in a worst-case scenario? I don't know if you've been in the Erlang real-time talk, 2 talks previously here, they were always talking about what's the worst case. Like, I have this time, and then the garbage collector can run this time, but I need to answer in that time. So then a worst case is maybe what you're looking for. This is an excerpt from the benchee HTML report. So there's also formatted to the HTML reports. And I ran sorting on lists of the size 100,000 elements, 10,000, a million, and 5 million. And I was actually just interested in the worst case, because it was a question if could I afford to sort this list. So I wanted to get a value that is very easy to compute if you have a sorted list. But it is possible to compute without a sorted list, which is it's much faster, but it's also very complicated. And I don't like complicated code. As long as I can get away with simpler code, I always prefer the simpler code. And we can see here that the maximum runtime that we sort of measured in our run, the worst case, even for 5 million elements, which I think I'll never reach in that particular use case, is still 2 seconds. And for my use case, because it's actually for benchee itself, it's okay. I said that like the user maybe waits for a couple more seconds. They ran a benchmark already. It's fine that they wait for that amount of time. Another question is also, did we make it faster? Or another phrasing of the question is like, what's the fastest way to do something? And there I have a little question, a little example I brought for you, is what's the fastest way to sort a list of numbers largest to smallest? So not ascending, but descending. Was that correct from your point? Yes. Okay, so I brought you a couple of examples. So we'll take a list that is 10,000 elements. We'll shuffle it really good so that we actually have some sorting to do. And then our first version is we sort the list, but we provide our own sorting function where we sort of switch around what is bigger or smaller. So a very custom sorting function. Second approach is we just sort it and then we reverse it. And the third option is a very clever option. Instead of doing any of these things, we sort by minus the value, because if we have a list of just positive integers, or probably all integers, then doing a minus really results in that reverse sorting that we were looking for. And now I'm looking for some audience participation. Who thinks that the first version is the fastest? 1 person, 2, 3, 4, or maybe people just don't like audience participation here. We'll see. Second option, first sorting and then reversing. Good 50% of the room, maybe. And third option, sort by minus the value. Yeah, another 20, 30%. And good audience. Sorting and then reversing is by far the fastest. And when I first encountered this, I was like, how could this be? Like, the other things are much more specialized. Like, did I do like an extra reverse step? How? Why? And the answer is most likely it's optimized already on the Erlang VM, because sorting can then just be implemented in C, and then reversing is also, because we need to do that a lot, especially with tail-recursive calls, tail-recursive functions. So it's all highly optimized. So oftentimes your intuition betrays you, because it looks like we're doing more, but it's actually more efficient. So
function application.
It's what?
Function application. Function
Yeah, exactly. You need to run that custom function a lot of times. Yeah, so that is a surprising result. So at that point, some of you might interject and say, wait a second, isn't that the root of all evil? I heard something like premature optimization, blah, blah, root of all evil, very, very bad. And for me, it's most likely that not reading the sources that you're trying to quote is the root of all evil. And I'm actually very happy because like almost everyone here like quotes a computer science paper, and so now I get to do the same. So that was written in a paper published in 1974 by Donald Knuth. And he says, we should forget about efficiencies, say about 97% of the time. Premature optimization is the root of all evil. So yes, he said that, that's true. However, if you just read the next sentence, he goes on to say, yeah, we should not pass up our opportunities in that critical 3%. And In the previous paragraph, he actually mentions that a 12% improvement easily obtained is never considered marginal. And what we're talking about here, what you've seen before, is way above a 12% improvement. But he touches upon a good point. Sometimes people just try to optimize everything without knowing that it's actually, hurtful for the application that this is particularly slow. So, in order for that, we need to talk a bit about sort of different types of benchmarks. So, who here is familiar with sort of the testing pyramid? So, unit tests, integration tests, the feature level tests? Most people are. I'll give it a quick run through. So, unit tests mostly test like one single function. Integration tests, a couple of modules or functions interacting together. And feature level tests are oftentimes even to the point where they are sort of independent from the language. So, for instance, you have web applications, you have a browser that drives through, clicks through the application, or maybe for some embedded device, you just send it the packages and then see if it returns the correct packages or changes something accordingly. And I have a benchmarking pyramid. That is not really official or anything, but it's how I think about benchmarks. So we have micro-level benchmarks that react on like the very small function level, which is most of what we've seen so far. We have macro-level benchmarks, which are sort of on the integration level. So if I talk web application, it's maybe like one controller or what one controller does. And we have application level benchmarks, which is what that Phoenix benchmark was, because they just had a couple of Zung, I think it's called, tools connected, or you have WRK that just sends requests to your web application and sees how fast they answer. So now what are the properties of these benchmarks, of these different types of benchmarks? First, obviously the number of components involved goes up. In a micro benchmark, you just have one function. You can be very certain that like you change something in that function, you change the performance metrics of the benchmarking outcome. But on the application level, like everything is involved. You have databases, you have the network, everything is there. Also at the same time, the setup complexity goes up. In that example of the Phoenix benchmark, they spent days doing it. I think they had more than 45 machines running to actually do all of this. It was very, very complex to do. So that's also the reason why I think they have never done it again, which is sad because we might have some performance regressions in there now and we just don't know about it. Whereas a micro benchmark is super easy to set up. At the same time, also execution time goes up because exercising the whole application obviously is more straining than just one little function. But at the same time, the confidence of real impact on the application level goes up because if I exercise a whole endpoint and its response time, then I know like, okay, if I make this twice as fast, then that endpoint is going to be twice as fast for my users. So that is very, very good. And I like that. Whereas when you do a micro-level benchmark, you might increase like your, your regex execution time. Your regex might get like 10 times faster, but that might be 10 microseconds faster for your whole request, and your whole request might take, 40 milliseconds to respond, so it doesn't really matter. And that's also a mistake I often see people make, like they make something 10 times faster, but by that they save maybe 10 microseconds or maybe even half a millisecond. But in the same but the application also does a database query that takes 10 milliseconds. So like what you gain there is so little, in the end it doesn't matter. And what also goes up is the chance of interference. So when I have an application level benchmark, the network could go wrong, the database could misbehave, all these things could happen to me. Whereas on a micro level benchmark, I just have my one single function, so I'm very, very certain. Also, Devin had a bit of a similar figure where we were on the spectrum from like left to right yesterday. And most of the time, when people show you these spectrums, they tell you, this is sort of the golden middle. This is where sort of the drawbacks and the good sides balance out a bit. So what I often do is when I do a benchmark, I do macro-level benchmarks. So I have a controller that I want to make faster, so I just take whatever service I have there, or the big function, I just execute that in a benchmark. Then I don't have all the interference, all the setup, but I still am very, very certain that what I did actually made things faster, or made them faster a lot. So let's finally talk about what good benchmarking looks like. And what does it look like? Well, at every benchmark, before you do it, there's a question. Like, what am I benchmarking for? What is my goal? So you want to make that endpoint faster because your users complain that that endpoint is slow, or you want to have as many connections to your Phoenix web server as possible at the same time. Those are all goals. You can just go out there and just benchmark for fun how fast sorting is or whatever. As a fun exercise, I sometimes do it because I'm very interested in it, but in the end, it doesn't really help your application to be as fast as it possibly could be. Another thing that people often forget is the system specification. Like, what machine was this run on? What version of Elixir? What version of Erlang? Or what version of Haskell? Whatever. People don't tell you these things, and they're an integral part of every benchmark, especially also if you're on the JVM. The JVM with new releases sometimes gets drastically faster. So there's benchmarks when you had like an initial implementation of a language on the JVM 1.0, and just through the new JVM versions, it would get 4 times faster. So it really matters which version it is on. And yeah, also CPU and RAM matter to an extent. Which is why benchee, when you run a benchmark with benchee, it prints out all these values. So you know what's the configuration, what was this run on. So if people just copy and paste the output of benchee somewhere, you can see exactly what's up. And I brought you 2 benchmarking examples. One uses map.flatten, so first maps and then flattens, and the other one uses our beloved flatmap. And in this example, flatmap is much, much slower than map.flatten. And here, flatmap is much, much faster. It's actually twice as fast. And it's the same benchmark. It's the same input size. Almost everything is the same. So how can this be? Well, the latter example is Elixir 1.4, and the former example is Elixir 1.3. And why? Well, I opened an issue and was like, hey, flatmap should be much, much faster than map.flatten. Like, what's up? This is like the only constant that I should know. That is how things should be. That's how it's in Erlang and Ruby and like every other language that I know. And then Jose took 18 minutes to look at the existing implementation, write 2 new implementations that were both faster. Then we benchmarked them. Everything is good. And then we had a nice speed improvement. So that's an example where like it's twice as fast now. So all the benchmarks from before without the version information, you can basically throw them away. Another thing that is very, very crucial is that you have a correct and meaningful setup. If you benchmark and you have a database and your database only has 1/10 or 1/100th of the records that you have in production, it doesn't really help you because you're really, really likely not to hit the performance problems that you would have on production. So the data needs to be shaped at least a little bit the same. Same goes for production environments. So especially lots of compiled language have a flag for optimization, like really optimize this code. That's usually not used in development. And oftentimes these optimization flags optimize a lot of the things away that you can optimize away locally in your development environment, but it doesn't matter because the compile optimization will do so for you. Also, it's very important that you have an interference-free environment. So don't have Slack running and your music player and your email inbox and your browser with 100 tabs open because that can really hit the performance of the benchmarks. I once accidentally benchmarked on a smaller laptop with Slack running and my results were half as fast than they were with when I shut Slack off. So there's a real impact there. I mean, it's partly Slack's fault, but that's another story for another day. That's also particularly true for logging. Especially on the Phoenix mailing list, often there were questions like, oh, Phoenix is much, much slower than advertised. How come? Why is this? Like, are you cheating or whatever? And it's like, oh, yeah, please run a production environment and set your log levels to production log levels or turn them off. So then you'll see these because actually file I/O is somewhat expensive. And it's all these things that people forget about and really make benchmarking often very, very hard, or specifically comparing different languages even. It's super hard. Another interesting thing is garbage collection. Most of our languages these days, save for like Rust, C, and whatever, are garbage collected. And that can have a real hard impact on your results because at some point the garbage collection hits. Here's a graph that graphs the raw runtimes of a benchmark. That's also put out by benchee HTML. And please note that down here, the bottom bar is actually 251, so it doesn't start at 0, so that we get a better look at things. And you can see all these spikes. And I bet with you some of these spikes is the garbage collector heading in, and that creates your maximum runtime. That also increases the standard deviation. Some of them might also be that, I don't know, Dropbox started, it wanted to sync, and thought it was very, very important right now. Yeah, so that's something to be aware of. Especially for micro benchmarks, garbage collection can make up a ton of the time. Now let's talk about Warmup. I mentioned it briefly in the beginning that benchee runs for a given warm-up time in the beginning. Why is this useful? I often see benchmarks like this in the wild, where you use the operating system time command and then execute the program, and that's your benchmark. And that's most likely not what you want. So unless you're writing a command line tool that you just run once for 1 second or for a couple of milliseconds and then it's good, then that's maybe what you want. But I think most of us are either working on web applications, embedded devices, or we're working on long-running systems. They're up for hours, days, weeks. So what I don't care about in the performance is how long it takes something to start, for instance. So when you measure like this, this is basically the time that you measure. And first you have a startup time, which might be very, very bad for instance, I mean, last time I checked, especially for Clojure and Scala, startup time was a bit bad, and Ruby it's also kind of bad. So do you want to measure that? No, like your servers start once and then they run for hours. Doesn't matter to me. And then there's this warm-up time where, especially if you have a JITted language, so with a just-in-time compilation, at first it actually gets slower because it does all this work to do the just-in-time compilation to get faster, but at first that makes it slower, obviously. And then afterwards we have the actual runtime, so that's what your system performs 99% of the time. That's what I want to measure. I don't want to measure the other stuff, unless that stuff for some reason is important to me, that startup time. For instance, Elixir and Erlang, we don't have a JIT, sadly. I mean, we're still very fast, but we don't have a JIT. But they're still important because, you know, the processes grow in memory, for instance, so you don't have as many garbage collections or like that growing off the thing. Maybe you need to start some processes in the beginning. Your database also starts to build up a cache or whatever, so that's why the warm-up time is important. And just as an example, so that you don't see like, oh yeah, warm-up time, it's maybe like, okay, it's maybe 20% slower or whatever. This is a benchmark that compares the MJIT Ruby implementation to Truffle Ruby, which runs on the Graal VM, which is a very advanced JVM, or it's now part of the JDK 9. In some parts. It's very, very advanced. It does lots of jitting, inlining, optimizations and whatever. And I mapped for you the raw runtimes of each individual run of a specific benchmark. And we can see that Truffle Ruby, for the first iteration, takes 28 seconds. It's super slow. And when you just measure this, you're like, oh, it's slow. Like, I don't care about this. This is pointless. But you see, as time progresses and as it jits and optimizes itself more and more, it gets much, much faster until in the end it only takes 2 seconds. So if we just measure the first iteration, we're like, okay, this is 3 times as slow as MJIT. But if we actually give it a warm-up time and then measure the last iterations, then we see, oh, it's actually 3 times as fast as MJIT. So there's a really wide spectrum here that you can hit with that. And it all depends on the method of measurement. So choose the method of measurement that really suits your use case or what you want to actually see, not just the results you want to see. Another thing that I found to be very, very important is that inputs matter. Your inputs are basically like this skyline of, what was it, New York or San Francisco? I forget. But like some of them are wide, some of them are tall, some of them are small, some of them are blocky, some of them are pointy. So point being, they're all very, very different. And you need to account for that in your benchmarks. You don't need to just benchmark with one input because your performance characteristics can be widely different. And for that, I have a little story time. And quick, is that Polish? Oh, I hope there's nothing too bad written there. Like, I don't speak Polish. I just can say smacznego, dziękuję, proszę. Anyhow, once on a very, very nice winter day, I was sitting there and was like thinking nothing evil when, boom, a Slack message with a bug snag popped up. And it went on and said like, Elixir DB connection. I was like, what is that? Why, like, my beautiful little Elixir application, how does it throw an error? It can't be. And I looked it up, and it was because Actor has a default. Actor is sort of like the database tool for Elixir. It has a default timeout of 15 seconds. So when a query takes longer, it throws you this nice error. It was like, 15 seconds for a query? What's happening? What am I doing wrong? What's up here? So I looked at the application, and for a little background, this is an application that tracks with a courier. So the courier from our Android application, which by the way is written in Scala, they push the GPS location to us. And then we have a WebSocket on the other side that connects to the Phoenix channel that receives these location updates. And when you connect to that socket, it tries to get you the latest location where the courier was so that you have one location that you can already look at. That was the code that was causing problems. It was like 15 seconds to get the location of one courier. What's up here? So I wrote a benchmark, naturally. And the solution that was in production at the time is the one above there. So we have a database view, latest courier location, which is basically a database view that has the latest location of each and every courier, and then we just look for the courier we want to have a look at, and then we get it. And then I wrote two different implementations. The only difference between the other two ones is this. The one at the bottom uses like a normal where courier ID is this query, and the other one uses a function that we wrote that basically ends up doing an array check with any. It's fine, but otherwise what they do is they order them by time descending so that we get the latest one, and then they just grab the latest one. So roll a benchmark. I found out that it was because we had 2.5 million of these locations because the client was misbehaving. But still, that's not too bad. Like, that's not something that Postgres can't handle. So we were running on Postgres 9.6. So it's like, was weird. And then I wrote this benchmark, and I see like, oh, wow, OK, my new implementations are much, much faster. So actually, the old implementation is 4,600 times slower. I was like, wow, it's like the best performance improvement I ever did. It's like, I was very proud of myself, you know? So again, this is obviously another job well done. So I implement this and very fast because I hate it when I see bugs. And I deploy it. And it goes boom. I was like, oh, wow. LXDB connection. I'm like, wait, I fixed you. I know this. Like, probably the old application is still running. Then another one is like, oh, maybe like because I'm deploying right now. And then boom, it's like, oh, what is happening? Holy, I shouldn't swear so much. And then it's like, what? So I roll back the changes, and I'm like, what's happening here? Like, I know, but I write a benchmarking tool. I benchmarked this. Like, what am I doing? How could this possibly go wrong? And so I went back, and I actually used multiple inputs, which funnily enough, I didn't do before. And this is the lesson to learn also for you. And so now I take a variety of courier IDs of couriers that have a differing amount of applications. So we not only take the big one with 2.3 or 2.5 million, we also take a courier that has no locations, 20,000 and 200,000 locations. Why did I do that specifically? Because when I looked at it, I saw that it was failing specifically for couriers that had no locations whatsoever in the database, which might happen because they don't use our app or they're external couriers or something like that. And what you can do in benchee, because I realized that was a very important thing. So we have a map of the input name to the actual input. Then you can say, benchee, please use these inputs. And then it will pass it into the functions, to benchmarking functions, where then can use them. And benchee will run it with all these different inputs. Now I run it, and I get these results a bit shortened for you. And we see that for the big list, we're the fastest by far. But when we go all the way down to no locations, we are 36,000 times slower than our database view implementation. We're just like, huh, who would have thought? Like, I didn't do the inputs before because I was like, OK, this is obviously the case that takes the most time. So I'm just going to benchmark this one. The other ones I don't care about because they will be faster. So when you encounter something like this, and it's basically not benchmarking Elixir, but benchmarking Postgres, you have a very neat tool that's explain analyze, which sort of says, like, dear Postgres, what do you think as a query planner do you want to do with this, and how does it actually pan out? And so I got the query from Ecto, put it into my Postgres shell, and then the first thing that we see is it does an index scan. Index scan is always good because we use an index, that's fast. And it says backwards using courier locations time index on courier locations. That's good. But what's not so good is then we have a filter condition that just says, OK, so it sorts them sort of backwards, and then it goes through like, are you my courier? Yes, no, 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 no. So if there's no locations in the database, it will basically go through the whole table and be like, are you my courier? No, 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 no. So we end up scanning the whole database with its millions of locations, basically, which is bad. Why is it that bad? At the time, we had two indexes, one on courier ID and one on time. And it decided for the sorting to just use the index on time, and it couldn't combine it with using the index on courier ID. What's the fix for that? The fix is actually pretty easy. There's something called combined indexes or multi-column indexes, where I can say, like, here you have an index on courier ID and on time. So, and then the leftmost is always the most important, the one that should have the equality condition and should do the most filtering. Then you can actually use both of them. So wrote a migration, added that index, removed the other two because I didn't need them anymore. And then these are the results. And we can actually, because of a new benchee feature where you can save the results of a previous benchmarking run that are now annotated with before here. By the way, I tweeted these slides if you want to have a look at them already. And we can see that now for no locations also our full custom implementation is the fastest. With courier IDs is very fast. And we just kick everyone else's ass, basically. For 20,000, we're still faster. For 200,000, we're also still faster. And also for the big 2.5 million, full custom is still the fastest. So that was a very hard lesson learned for me, and why do I need all these inputs? Talking about inputs, so now we found an implementation that is fastest overall for all the inputs I could think about. But let's talk about tail call optimization. So for those that don't know, tail call optimization is if you have a recursive function call, so the function to itself, and if that's the last call and it's super fast, and yay, we're all happy. First, let's look at what a body recursive function is. And so we implement map, and the map of the empty list is the empty list, and the map of a list that has something applies the function to the head and then calls itself on the tail and so on and so forth. Why is this not tail recursive? Because the last, call to map body, because the last call actually is this list prepend operation. So that's why it's not tail recursive. Now to the tail call optimized version. This is the function, and then we have our own internal function, do map TCO, because we need to add an accumulator to all of this to sort of get our results in the way, because they're in the wrong order. So if of the empty list, we will just return the accumulator. And when we don't have that, we call ourselves. We are the last call. Nothing else happens. We take the head, and we prepend the result of applying the function to the head to the accumulator. And then we go on. But because we're then backwards, because the first is the last, we need to reverse the list. And I brought you another little example. Take this implementation, and I changed the argument order around. So now the list is the first argument, and not the accumulator anymore. I'll call that do map TCO argument order, and we'll see what happens. So this is the benchmark again. Up here we have a variety of inputs from 10,000 elements in a list to 5 million. And then we have our implementations. The tail recursive one, I put in the standard library map, body recursive, and the one where the argument order is reversed. Or reversed is different. So let's have a look at the results. And we can see that for smaller inputs, actually the standard library map and the body recursive one are faster than our tail recursive ones pretty consistently. That's the first really interesting thing that we notice. Only when we get into bigger territory, 5 million, 10 million, and so on, only then is the tail recursive call faster, which was fascinating to me because I always thought, like, if I can make a tail recursive, I should, because it's optimized and it's obviously much, much faster. Isn't always the case. And the other thing that we notice is that the one with the reversed argument order is always faster than the normal tail recursive one. And why is that? And thankfully, Michał told me yesterday there's a special optimization in the Erlang VM for like the first argument is like a list destruction or whatever you get ahead. There's a special performance improvement for that, compile optimization. But he also told me that in Erlang 21, it will be optimized for all points. So this, again, will not be useful much anymore if you run on BeamVM 21. Can I have a look at the graphs? And there we see it. Yep. Much, much faster unless we have a very big input. Now you might ask, because tail optimization, what about memory? Like, we don't only care about runtime. I said this is mostly going to be about runtime, not about memory. So right now we have a pull request by Devin to add memory measurements to benchee. We have lots of help also from Michał to figure out how we best do that. And let's see how memory scales with that. And what we can see is that the tail recursive versions, because they also need to build up that accumulator list and then also do the additional reverse, are oftentimes much, much worse memory-wise as well. So in our big example, they are the fastest, but they also take twice as much memory as our body recursive functions. So is tail recursion bad? No, obviously not. This is just one example. It could be very different in another example. And also, very importantly, if you have a function that has to run all the time so that it never finishes, like in a gen server or something, without tail optimization, everything will blow up. So it's still very important and very good, but just don't take it as like a grounded knowledge that this is always what you should do. So nearing the end of the talk, what even is a benchmark? It's not just bunnies eating stuff. It's also something else. And I found a very good answer for myself when I was designing benchee. So this is also an official interface in benchee. You can use it. And this is sort of the steps that, in my mind, a benchmark goes through. First, we have some sort of a configuration that tells me like the warm-up time and a bunch of other things. And that I just take and initialize benchee with it. Then I gather a bunch of system data. So I can see like, OK, this is on this CPU, this Elixir Erlang version, whatever. Then I define my benchmark. So I have a job. And then the function, whatever it does, I might have a bunch of those. Then I measure. So then I get all the raw runtimes, all the raw memory measurements. Then we compute statistics based on those. So Sally didn't get to talk to you about statistics, but we have cool statistics like maximum, minimum, 99th percentile, median. We also draw box plots, for instance. And then when I have all these statistics, I can go through different formatters that just print them out in a different format. So we have formatters for like the console formatter that is built in, HTML, JSON, and CSV. So that's all the information you can get, and that's how a good benchmark should look like, in my opinion. Before I leave you here, I really want to encourage you to run your own benchmarks. Don't trust just people that put it online or somewhere and then trust like, oh, this is faster, this is what I should always do. Your environment might be different. Your use case might be different. Everything else might be different. Like the benchmark might have been run with an old Elixir or Erlang version. You might not really care about it. So please run your own benchmarks. Check them into your Git repository. We have a benchmarks folder that has the benchmarks and also sort of as a comment the last result when we ran it the last time. So at any given time, they can be rerun against new library versions, against new inputs or whatever. So you can always see, is our assumption from back then that this is the fastest, this is still the fastest. And then, without further ado, please enjoy benchmarking.
Hi there, thanks for the lecture. One question, the benchee tool that you're presenting is just for Elixir or it can be used for benchmarking on Erlang?
On what?
On Erlang, on the base.
Like for databases, you can use it as long as you have an apparent Elixir or Erlang driver for it. But generally, it executes Elixir code. So usually it's used for benchmarking Elixir code. But like the database was just a fun thing that you can also do with it and get good results out of it.
All right, thank you.
No, he's coming to you, I think.
Yes, yes. How do you determine the warm-up time of the thing that you are benchmarking?
Right now, it's set in the configuration, so it's not dynamic or anything. So the default is 2 seconds, but you can set it to whatever. It's basically then experience. So if you see a benchmark and you run it and there's a high standard deviation, try to increase the warm-up time. But there is approaches where you can have a confidence interval where you can say like, okay, I want to have this with this and that confidence. And then you can basically benchmark for the time that you need for that. And you can take measurements to like how big is my standard deviation and then do it afterwards. That's not implemented yet. But that's an idea I have for far in the future. But I have way too many ideas for benchee and does so many things already. And it's still in the pre-1.0 version because I always want I want to have this other feature before we go 1.0. And I don't want to break compatibility for for all the plugins. So I really need to, Devin really needs to shut me up and then be like, okay, we release 1.0 now. So yeah.
Okay, thank you.
Okay, I think we have time for one last question.
Hi, I'm planning to add continuous integration support, like to see if some function was broken and started, and like to detect performance degradation?
It's a very interesting question that I get a lot, and it's very hard because oftentimes your CI servers are very overloaded, and so then the times fluctuate greatly. So ideally what you want to have is you want to have like one server that just sits there, is all alone, and then executes your benchmarks. But for, what was the event called, Mihao? Spawnfest, thanks. Mihao for Spawnfest actually built a service, like as a service that sort of does that for you. You define your benchmarks and it runs them. But I think it just plots them, right? Yeah. And so what I like as an approach for that is that you don't fail the build immediately because it might have been some interference, but you plot the results so then you can see a trend. If there was just one spike once, maybe something was wrong with the service, and then it's back again. But if it's consistently high up after a point and you see you have a problem, you have the build number, the commit hash, whatever that introduced the problem, you look at it, you fix it. That is sort of my preferred approach.
Okay, thank you once again.